Matrix inversion is a fundamental operation in wireless communications, especially critical for the multiple input, multiple output, or MIMO, systems central to 5G and 6G technologies. It's essential for tasks like precoding, equalization, and channel estimation, which are vital for combating interference and optimizing data transmission. However, the computational cost of matrix inversion, scaling as O for an NXN matrix, poses a significant challenge. This cubic complexity means that even a small increase in matrix size leads to a disproportionately large increase in computation. For instance, Gaussian elimination or LU decomposition, common methods for inversion, directly exhibit this O behavior. In contrast, a matrix vector multiplication scales much more favorably at O, highlighting the unique burden of inversion. This complexity is dramatically amplified in 5G's massive MIMO systems, which utilize numerous antennas at the base station. With 64 to 256 base station antennas, these systems generate large matrices, often 256 by 256 or larger, that require inversion. Crucially, these inversions must occur in real time, often within short coherence intervals measured in milliseconds, to adapt to rapidly changing wireless channels. This real-time demand for large matrix inversions leads to significant power consumption and introduces critical latency issues. The challenge intensifies with 6G, which envisions ultramassive MIMO systems with over 1,000 antennas. Operating in terahertz bands, 6G will involve even higher dimensional matrices and demand stricter latency requirements, often in the microsecond range. This pushes the computational boundaries to an unprecedented degree, making efficient matrix inversion an even more pressing concern. Consider zero forcing, or ZF, precoding, a technique that relies on inverting the channel matrix H to eliminate inter-user interference. Another example is the MMSE receiver, which requires inverting a matrix of the form for optimal signal detection. To illustrate the scale, a simple 2 by 2 matrix inversion involves only a few floating point operations. However, for a 256 by 256 matrix, this jumps to millions of flops, and for a 1000 by 1000 matrix, it's billions, all within milliseconds. To address this, researchers are exploring approximations like conjugate beamforming, which avoids explicit matrix inversion. Iterative methods, such as the conjugate gradient algorithm, also offer more computationally efficient alternatives by converging to an approximate solution. These advancements are vital for the performance and efficiency of future wireless networks, driving the need for specialized hardware. Ultimately, overcoming the expense of matrix inversion will be key to unlocking the full potential of 5G and 6G communications.